Welcome to another deep dive. I've been looking forward to this one. It's the logic of action.
Oh, good one.
Yeah. And this is going to be great for our philosophy listeners, because it's really about using formal logic to understand what it means to act.
Right, exactly. And what's really cool about this is it's not just philosophy. I mean, it draws from linguistics, computer science, AI. All these different fields have a perspective on this.
Yeah. Yeah, and it makes sense, right? I mean, if you're thinking about, like, what do we even mean by knowledge, or how do we communicate, or even how do we build intelligent systems, the concept of action is right there at the center of it all.
Absolutely. How can we talk about things like ethics or responsibility or even free will without first having a solid grasp on what it means to act?
Exactly. Exactly. And that's what we're going to do today. We're going to kind of unpack all of this. And our main source is the Logic of Action entry from the Stanford Encyclopedia of Philosophy.
Great resource. Really comprehensive.
Yeah. It's a good one. It's a good one. So what we're going to do is we're going to start, naturally, with the philosophy of action. See how modal logic played a key role in shaping the field, leading to theories like Stitt theory, dynamic logic.
Right. And then from there, we'll branch out and see how linguistics tackles action, both in terms of speech acts, where utterances themselves are actions, and in how we use language to describe action more broadly, which gets us into dynamic semantics.
Yeah, yeah. And then we'll make our way to computer science, which, as you can imagine, heavily relies on logic of action. I mean, that's how you make sure programs actually do what they're supposed to do.
Exactly. Program verification,
Yeah.
making sure your code works, that all comes down to understanding actions and their consequences.
Absolutely. And finally, we'll wrap up with AI. I mean, if you're going to build intelligent agents, you need to figure out how to represent action in a way that makes sense.
Right. And the Stanford Encyclopedia entry actually does a good job of covering the different approaches to that, from situation calculus to BDI logics, well, all kinds of interesting stuff.
So it's going to be a really fascinating journey, I think, for anyone interested in the logic of action, but especially for our philosophy listeners.
Yeah, definitely. A lot of connections back to those core philosophical questions.
All right. Well, let's dive in, starting with the philosophical foundations.
Sounds good.
So, the idea of using formal logic to analyze action, this isn't new. Actually, there were hints of this way back in the Middle Ages with St. Anselm. He was grappling with the concept of God's actions and how they relate to human freedom.
Right, right. But of course, back then, they didn't have the same logical tools that we have today. So it wasn't until the 20th century that things really started to take shape.
Yeah. And there are a few key figures who really laid the groundwork. Anderson, Fitch, Kanger, von Wright, they all made significant contributions. But it was Celles who really systematized things, providing the first comprehensive semantic account of action in modal logic.
Yeah, Tellus was crucial. He really set the stage for what came next.
Okay. So, from that foundation, two main families of theories emerged in philosophical logic of action: Stitt theory and dynamic logic.
Right. And each takes a slightly different approach to representing and reasoning about action.
So, let's start with Stitt theory. It's a kind of a weird name, isn't it?
Yeah, a little bit. It's actually short for sees to it that.
Sees to it that.
Yeah.
Okay.
So basically, the idea is that you have an agent, and that agent, well, they see to it that some proposition becomes true. They bring it about through their actions.
Okay. I'm starting to see it now. So you've got this agent, they take some action, and that action makes something happen.
Exactly. And Stitt theory provides a formal language for representing all of that.
All right. Well, how does it do that?
So they introduce this new operator into propositional logic. It's written as Stitt, followed by the agent, and then the proposition that they see to it that. So, for example, if we want to say that agent I sees to it that phi becomes true, we'd write Stitt sub I phi.
Stitt sub I phi. Okay, so that's the basic notation. But what about the semantics? I mean, what does it actually mean for an agent to see to it that something happens in this framework?
Right. Well, that's where things get really interesting. Stitt theory uses a branching time framework, where you have these moments in time, and at each moment there are multiple possible future histories.
Okay, so kind of like a tree where the past is fixed, but the future branches out in different directions.
Exactly. And the agent's actions influence which of those future branches actually gets realized.
Oh, okay. I see. So it's all about the agent's choices and how they shape the future.
Exactly. And to represent this formally, Stitt theory uses something called a choice function.
A choice function.
The choice function basically divides up the set of possible futures at any given moment into these things called choice cells.
Choice cells.
Yeah. And each choice cell represents a different action that the agent could take.
Okay, so like at this moment, I have a choice to keep talking or to take a sip of water. And each of those choices would correspond to a different choice cell.
Precisely. And the agent's choice, the choice cell they select, determines which possible futures are still accessible.
So the choice function sort of narrows down the possibilities based on the agent's actions.
Exactly.
So we've got moments in time, branching futures, and choice cells representing the agent's actions. What else is there in a Stitt frame?
Well, we need to consider the agents themselves, right? So there's a set of agents in a frame.
Okay.
And then we need a way to evaluate the truth of propositions at different moments in time and in different histories.
Mm-hmm.
So that's where the valuation function comes in.
Okay. The valuation function.
Yeah. It basically tells us whether a given proposition is true or false at a particular moment in a particular history.
All right. So we've got all the pieces of the puzzle now. We have the moments, the branching futures, the agents, the choice function, and the valuation function. But we still need to figure out how the Stitt operator works.
Right. The Stitt operator is really the heart of the theory. Yep. And it turns out there are actually two main interpretations of it: cellist Stitt and deliberative Stitt.
Two different versions of Stitt. Okay, tell me about them. What's the difference?
Well, cellist Stitt, sometimes called Stitt for short, says that Stitt sub I phi is true if and only if phi is true in all the histories within the agent's choice cell at that moment.
Okay, so the agent's action guarantees that phi will happen no matter what else happens in the future.
Exactly.
Okay. And what about deliberative Stitt?
Deliberative Stitt, sometimes called distit, adds an extra condition.
Oh, okay. What's that?
It says that not only must phi be true in all histories within the agent's choice cell, but it also must not have been historically necessary.
Historically necessary.
Meaning that it wasn't already guaranteed to happen, regardless of what the agent did.
I see. So the agent's action must actually make a difference. It can't just be something that was going to happen anyway.
Exactly. Deliberative Stitt really captures that idea of agency, of the agent genuinely bringing something about.
So, in cellist Stitt, the agent's action makes phi inevitable. In deliberative Stitt, the agent's action makes phi happen, but it could have been otherwise.
Yeah, that's a good way to put it.
Okay, and the text mentions that these two versions of Stitt are actually interdefinable, right?
Yeah, they can be defined in terms of each other using the notion of historical necessity.
Historical necessity.
Which is basically the idea of something being true in all possible histories.
I see. So you can say that deliberative Stitt is just cellist Stitt plus the negation of historical necessity.
Exactly, and vice versa.
Okay. So that's Stitt theory in a nutshell. We've got the basic framework of branching time, choice functions, and the two versions of the Stitt operator.
Right. And from a philosophical standpoint, it's really interesting to see how Stitt theory tries to formally capture the idea of agency, choice, and the openness of the future.
Yeah. Yeah, I can definitely see the connections to discussions about free will and determinism.
Absolutely. And the text also mentions that Stitt theory has been extended to handle group actions, which raises all sorts of fascinating questions about collective agency and shared intentions.
Okay, well, we'll definitely have to come back to that in another deep dive. But for now, let's move on to the other major theory in philosophical logic of action, dynamic logic.
Sounds good.
So the key difference between dynamic logic and Stitt theory is that dynamic logic explicitly includes actions or events in its ontology.
Right. Unlike Stitt theory, which focuses more on the states of affairs that agents bring about, dynamic logic treats actions themselves as first-class citizens.
So you're not just talking about what's true or false before and after an action, you're actually talking about the action itself.
Exactly. And it turns out that this approach has its roots in computer science.
Oh, really?
Yeah. Dynamic logic was originally developed to analyze the behavior of computer programs.
That makes sense. I mean, programs are essentially just sequences of actions.
Right. And dynamic logic provides a way to reason about how those actions change the state of the computer.
Okay. So how does that work?
Well, it starts with the idea of a state.
A state.
Yeah. A state is basically a snapshot of the computer at a particular moment in time.
Okay.
It includes things like the value stored in memory, the status of the processor, the files on the hard drive, all the things that describe the computer's current configuration.
Okay.
And then actions are seen as functions that take one state and produce another state.
So if the action is add 1 to the variable x, then the state before the action might have x equal to 5, and the state after the action would have x equal to 6.
Exactly.
Okay, I'm starting to see how this works. So dynamic logic provides a way to talk about these state transitions and to reason about the effects of different actions.
Precisely.
And the text mentions that this approach has been generalized beyond just computer programs, right?
Yeah. Dynamic logic can be applied to any system that undergoes state transitions as a result of actions.
So it could be used to model physical systems like the movement of objects or even social systems like the interactions between people.
Exactly. It's a very general and powerful framework.
All right, so we've seen two different approaches to the philosophical logic of action, stit theory and dynamic logic.
Right. And each one highlights a different aspect of what it means to act.
Yeah. Stit theory emphasizes the agent's choices and their role in shaping the future, while dynamic logic focuses on the actions themselves and how they transform the state of the world.
Exactly. And it's interesting to see how these ideas from logic have also influenced other fields, like linguistics.
Let's move on to linguistics then. I'm really curious to see how they handle the concept of action.
Yeah, there's a lot of interesting stuff there.
Okay, so the text points out that actions play a dual role in linguistics.
Right. First, there's the idea of utterances as actions.
Yeah, speech acts.
Exactly. And then there's the way language is used to talk about actions.
Okay, so two different ways that action comes up in language.
Precisely.
So let's start with speech acts. I think most philosophy listeners are probably familiar with the basic idea, but maybe you can give us a quick refresher.
Sure. So the basic idea, as pioneered by Austin and Searle, is that when we use language, we're not just describing the world, we're actually performing actions.
Right. It's not just about truth and falsity. It's about doing things with words.
Exactly.
And they actually distinguish between several different types of speech acts, right?
Yeah, Austin's original threefold distinction was between the locutionary act, the illocutionary act, and the perlocutionary act.
Okay, remind me, what were those again?
So the locutionary act is just the act of uttering the words themselves.
Okay.
The illocutionary act is the force or intention behind the utterance.
Okay, so like when I say I promise to do the dishes, the locutionary act is just me saying those words, but the illocutionary act is me making a promise.
Exactly. And then the perlocutionary act is the effect that the utterance has on the listener.
So in the case of the promise, the perlocutionary act might be that the listener now believes that I'm going to do the dishes.
Right. Or maybe they feel relieved because they were worried about having to do the dishes themselves.
Yeah. So the perlocutionary act really depends on the context and the listener's reaction.
Exactly.
Okay. And the text focuses mainly on illocutionary acts, right? Because those are the ones that are most directly connected to the speaker's intentions.
Right. Illocutionary acts are really the core of speech act theory.
Okay. And Searle and van der Wecken actually developed a formal logic for analyzing these acts, right?
Yeah. They called it illocutionary logic.
Illocutionary logic.
And it's quite complex, actually. They identified 7 different elements that define an illocutionary force.
7 elements. Wow. Okay, I'm going to need you to break that down for me.
Sure. So the first element is the illocutionary point,
The illocutionary point.
which is basically the basic purpose or aim of the speech act.
Okay, so for a promise, the illocutionary point would be to commit to doing something in the future.
Right. And then there's the mode of achievement,
The mode of achievement.
which is how the speech act achieves its illocutionary point. And then there's the degree of strength, which is how strong or forceful the speech act is.
Okay.
And then there are propositional content conditions, which are the conditions that must be met for the propositional content of the speech act to be well formed.
Okay.
And then there are preparatory conditions, which are the conditions that must be met for the speech act to be appropriately performed in the first place.
Okay.
And then there are sincerity conditions, which are the conditions that must be met for the speaker to be sincere in performing the speech act.
Okay.
And finally, there's the degree of strength of sincerity, which is how sincere the speaker is in performing the speech act.
Wow, 7 elements. That's a lot to keep track of.
Yeah.
And they actually classified illocutionary points into 5 basic categories, right?
Right. Assertives, commissives, directives, declaratives, and expressives.
5 categories. Okay. So assertives are about stating facts or beliefs. Commissives are about making commitments. Directives are about trying to get someone to do something. Declaratives are about changing the world by saying something. And expressives are about expressing feelings or attitudes.
Exactly.
That's pretty comprehensive.
Yeah. But as the text points out, this very detailed and structured approach to speech acts has faced some challenges.
Oh, really?
Yeah. It turns out that it's actually quite difficult to predict the illocutionary force of an utterance just by looking at its grammatical form or its propositional content.
Yeah, I guess that makes sense. I mean, context plays a huge role in how we interpret utterances.
Exactly. And that's led to a shift in focus towards what are called update models of meaning, also known as dynamic semantics.
Update models, dynamic semantics.
Yeah. The basic idea here is that the meaning of an utterance is not just its truth conditions, but also its potential to change the knowledge state of the participants in the conversation.
Okay, so it's not just about what the sentence says, but about how it affects the listener's beliefs and knowledge.
Precisely.
Okay, that makes sense. But before we get into dynamic semantics, the text also discusses how linguistics handles action sentences.
Right. How we use language to describe actions and events in the world.
Yeah, so the standard approach apparently goes back to Davidson.
Yeah, Davidson's event-based account of action sentences.
Event-based. Okay, so what's the basic idea here?
Well, the idea is that action sentences aren't just about agents and objects, they're also about events.
Events.
So, for example, if you say Brutus stabbed Caesar, you're not just saying something about Brutus and Caesar, you're also saying that there was this event, a stabbing event, that involved Brutus as the agent and Caesar as the patient.
Okay, so the sentence asserts the existence of this event, this stabbing event.
Exactly. And this event is seen as a distinct entity with its own properties and relations.
I see. So it's not just a matter of Brutus having the property of stabbing Caesar. There's actually this separate entity, the stabbing event, that mediates between them.
Precisely. And this event-based analysis has been extremely influential in linguistics.
Yeah, it makes sense. It provides a way to capture the temporal structure of events, the roles of different participants, and all sorts of other nuances.
Exactly.
And the text mentions that this analysis also connects to Wendler's classification of verbs, right?
Right. Wendler distinguished between 4 basic types of verbs: states, activities, accomplishments, and achievements.
4 types. Okay, remind me what those are again.
So states are verbs that describe static situations like know, believe, or own. Activities are verbs that describe ongoing processes like run, walk, or read. Accomplishments are verbs that describe events with a definite endpoint, like build a house or write a book. And achievements are verbs that describe instantaneous changes to state, like win the race or find the key.
Okay, 4 different ways of describing what verbs do.
Exactly. And these categories have been very useful for understanding various linguistic phenomena like aspect,
Aspect.
which is basically about how we view the temporal structure of an event,
Okay,
like whether it's completed, ongoing, or repeated.
I see. And the text also mentions this idea of an incremental theme, which is related to the way we describe the progress of an event.
Right. The idea is that certain verbs, like write a letter or build a house, have this incremental theme, which is some entity that changes gradually as the event unfolds.
So in the case of write a letter, the incremental theme is the letter itself.
Mhm.
As you write more of the letter, it becomes closer to being complete.
Exactly.
Okay, so we've seen how linguistics handles speech acts and action sentences.
Right. But we still haven't talked about dynamic semantics.
Yeah, let's get into that now. How does dynamic semantics provide a different perspective on meaning?
Well, as I mentioned before, the key idea is that the meaning of an utterance is not just about truth conditions, but also about how it updates the listener's knowledge state.
Okay, so it's about how the utterance changes what the listener believes or knows.
Exactly.
And this leads to a different way of thinking about propositions.
Right. Instead of viewing propositions as static descriptions of the world, dynamic semantics sees them as instructions for updating a knowledge base.
Okay, so it's like a proposition is a recipe for changing your beliefs.
Exactly.
Okay, I think I'm starting to get it. So how does this work in practice?
Well, imagine that you have a knowledge base, which is basically a set of propositions that you believe to be true.
Okay.
And then someone utters a sentence.
Okay.
The meaning of that sentence in dynamic semantics is a function that takes your current knowledge base and produces a new knowledge base.
Okay, so the utterance transforms your beliefs.
Exactly.
Okay, I see. And this framework can actually explain some interesting linguistic phenomena.
Right. Like the difference between these two sentences, it rains, it may not be raining, it may not be raining, it rains.
Yeah, the first one sounds kind of weird, right?
Exactly. And that's because in the first sentence, you're first updating your knowledge base to include the proposition, it rains, and then you're immediately saying, it may not be raining, which contradicts what you just said.
Okay, so the first sentence leads to an inconsistent knowledge base.
Exactly. Whereas in the second sentence, you're first saying, it may not be raining, which doesn't actually add anything to your knowledge base, and then you're saying it rains, which does add something to your knowledge base.
Okay, so the second sentence is fine because it doesn't lead to any contradictions.
Exactly.
Okay, that's pretty neat. So dynamic semantics provides a way to account for the way that utterances change our beliefs. And it can even explain why some sentences sound strained while others sound fine.
Precisely.
And the text mentions a specific formal system called dynamic predicate logic, or DPL.
Right. DPL is a logical system that was specifically designed to capture the dynamics of meaning.
Okay, so how does it differ from regular predicate logic?
Well, one of the key differences is that in DPL, quantifiers can have a dynamically changing scope.
Dynamically changing scope.
Yeah. So, for example, if you say a man walks, the existential quantifier, a man, introduces a new discourse referent,
A discourse referent.
which is basically a placeholder for the man that you're talking about.
Okay.
And this discourse referent can then be picked up by subsequent pronouns or other expressions.
So you could say he is wearing a hat, and the pronoun he would refer back to the discourse referent that was introduced by a man.
Exactly. And in DPL, the scope of that discourse referent can extend beyond the sentence in which it was introduced.
Okay, so it's like the meaning of the sentence can actually change the context for subsequent sentences.
Precisely.
Okay, I see how that captures the dynamic aspect of meaning.
Exactly.
All right, so we've covered a lot of ground in linguistics, from speech acts to action sentences to dynamic semantics.
Right. And now it's time to shift our focus to computer science.
Okay, computer science. I know you're excited about this one.
Yeah. For a computer scientist, the logic of action is absolutely essential. I mean, computer programs are fundamentally about performing actions.
Right. Every line of code is basically an instruction to do something.
Exactly. And if you want to make sure that those programs do what they're supposed to do, you need a way to reason about the effects of those actions.
So it's all about program verification, making sure that your code is correct and doesn't have any bugs.
Exactly.
Yeah.
And that's where logic comes in.
Okay. So how do computer scientists use logic to reason about programs?
Well, there are a few key approaches.
Okay.
One of the earliest and most influential is Hoare logic,
Hoare logic.
named after Tony Hoare, who developed it in the late 1960s.
Okay. What's the basic idea behind Hoare logic?
So the idea is that you have a program, and you want to prove that it satisfies certain properties.
Okay.
And to do that, you use these things called Hoare triples.
Hoare triples.
Yeah. A Hoare triple consists of three parts: a precondition, a program statement, and a postcondition.
Okay, I see. So it's like saying, if this is true before the program runs, then this will be true after the program runs.
Exactly.
Okay, and what are the preconditions and postconditions?
Well, they're basically logical statements about the state of the computer.
Okay.
So, for example, a precondition might be something like x is greater than 0, and a postcondition might be something like y is equal to x plus 1.
Okay,
And then the program statement would be the part of the code that you're trying to verify.
I see. And the Hoare triple would say that if x is greater than 0 before the program statement runs, then y will be equal to x plus 1 after the program statement runs.
Exactly.
Okay, so that's how you use Hoare triples to specify what the program is supposed to do.
Right. And Hoare logic provides a set of rules for reasoning about these triples.
Okay.
So, for example, there are rules for sequential composition, conditional statements, loops, and so on.
Okay.
And by applying these rules, you can prove that a given Hoare triple is valid, which means that the program does indeed satisfy the property that you're trying to verify.
Okay, that sounds pretty powerful. So you can use Hoare logic to prove that a program is correct even before you run it.
Exactly.
All right, so that's Hoare logic. But the text mentions that it's been generalized into something called dynamic logic.
Right. Dynamic logic is basically a modal logic that's specifically designed for reasoning about programs.
Modal logic. Okay. So how does that work?
Well, in modal logic, you have these modal operators that modify the truth of propositions.
Okay.
Like the box operator, which means it is necessary that, and the diamond operator, which means it is possible that.
Right.
And in dynamic logic, you have a modal operator for each program statement.
Okay.
So, for example, if S is a program statement, then the modal operator S means after executing S.
I see.
And you can use these modal operators to express things like Hoare triples.
Okay.
So the Hoare triple PSQ can be expressed in dynamic logic as P implies SQ.
P implies SQ. Okay.
Which basically means that if P is true before executing S, then Q will be true after executing S.
Okay, I see. So dynamic logic is a more general framework that encompasses Hoare logic.
Exactly.
And it turns out that dynamic logic has applications beyond just program verification.
Right. It can be used to reason about any system that undergoes state transitions as a result of actions.
So it could be used to model physical systems or social systems or even linguistic phenomena.
Exactly.
Okay. And the text mentions a few other logics that are relevant to computer science, right?
Yeah, like propositional dynamic logic, or PDL,
PDL.
which is a simplified version of dynamic logic that's often used for reasoning about programs with loops.
Okay.
And Hennessy-Milner logic,
Yeah.
or HML,
HML.
which is a logic that's specifically designed for reasoning about concurrent processes.
Okay.
And Dijkstra's weakest precondition calculus,
Dijkstra's weakest precondition calculus.
which is a way of calculating the weakest precondition that must hold in order for a program to achieve a desired postcondition.
Okay.
And temporal logic,
Temporal logic.
which is a logic that's specifically designed for reasoning about systems that change over time.
Okay, so there's a whole family of logics that are used in computer science to reason about programs and other dynamic systems.
Exactly.
All right. Well, I think we've covered the basics of logic of action in computer science.
Yeah. We've seen how computer scientists use logic to specify, verify, and reason about programs.
And now it's time to move on to our final area, artificial intelligence.
AI.
So how does the logic of action play a role in AI?
Well, as you know, the goal of AI is to create intelligent systems.
Right. Systems that can think and act like humans.
Exactly.
Mhm.
And one of the key challenges in AI is figuring out how to represent actions in a way that makes sense for intelligent systems.
Okay. So how do you represent actions for an AI?
Well, there are a few different approaches.
Okay.
One of the most common is to use a formalism called situation calculus.
Situation calculus.
Yeah, it's basically a way of representing the world as a set of situations. And each situation is a snapshot of the world at a particular moment in time.
Okay.
And actions are seen as functions that take one situation and produce another situation.
Okay, so it's similar to the way that dynamic logic represents actions as state transitions.
Exactly.
Okay. And what are the advantages of using situation calculus?
Well, one of the main advantages is that it allows you to represent the effects of actions in a very clear and concise way.
Okay.
So, for example, you can use situation calculus to represent the fact that if you pick up a cup, then the cup will be in your hand.
Okay.
And you can also use it to represent more complex effects, like
Yeah.
the fact that if you drop a fragile object, then it will break.
I see. So you can use situation calculus to model the physics of the world.
Exactly.
Okay. And how do you actually use situation calculus to build an AI?
Well, one way is to use it to develop planning systems.
Planning systems.
Yeah. Planning systems are AI systems that can figure out how to achieve a goal by performing a sequence of actions.
Okay.
And situation calculus provides a convenient framework for